Alright, so before we get into actually deriving the equations to describe our longitudinal forces and moments, we need to just recap a couple of key concepts and ideas, starting with the concept of a trim condition. So trimming the aircraft is essentially all to do with relieving the workload on the pilot and getting the aircraft to maintain a specific flight condition on its own, right? So if we take the example of the elevator, so let's say the pilot is having to pull back on the stick inside the cockpit in order to maintain a particular elevator angle and therefore maintain a particular flight condition. Well, instead of having to maintain that backwards pressure on the stick, the pilot can use what's called a trim tab, which operates in the opposite direction as the elevator, and basically causes the elevator force to be counteracted and keeps the elevator in the same position as it was with the pilot maintaining the force on the stick. So the idea behind this is again to do with moments, right? So the elevator is exerting a downwards force to maintain the aircraft with a nose up attitude, right? And it has a particular moment arm associated with it with regards to where the force acts and where the fulcrum point of the elevator is. You can see that in the bottom left hand diagram on this slide. And the trim tab exerts a force in the opposite direction because it moves in the opposite direction as of the elevator, but exerts a much smaller force. But because the moment arm associated with that lift vector is longer than the one that's exerted that's associated with the force exerted by the elevator itself, then the force and therefore the trim tab can be much smaller in size, right? So the trim tab essentially makes the elevator maintain its angle and therefore maintains a particular flight attitude and therefore flight condition for the aircraft. So by using the trim tab, you can see in the right hand figure here the elevator angle eta and the trim tab angle, which is called beta in this figure, essentially leads to a particular stick force as experienced in the cockpit by the pilot, and by setting the trim tab in the correct place essentially relieves the force on the stick inside the cockpit and maintains the aircraft in a particular flight condition. So in general, all control surfaces can have a trim tab. You can have aileron trim, rudder trim, and it's a very common practice to manipulate those controls in order to relieve the workload for the pilot. So next we should discuss what's called the stability axis system. I've mentioned this briefly before, but essentially the stability axis system is the one that we're going to use to model the longitudinal forces and moments, because it's convenient for us to rotate the body axis system and adjust the body axis system for angle of attack, because it makes our math a little bit easier when we come to look at how the aircraft is essentially changing its attitude and its position with respect to that axis system. So all of the equations of motions that we derived in chapter 1, they're all still applicable, they're all still valid, but we've just rotated them with respect to what we're going to call the trim angle of attack. So the first thing to note with this diagram is that all of the trim condition parameters have all got subscript 1s, right? So that's alpha 1, the trim angle of attack, gamma 1, which is the trim climb angle, and then the sum of those two, which is theta subscript 1, which is the pitch angle. So just to recap what they are, alpha 1, which is the trim angle of attack, is the angle between the body axis system, x-axis, and the flight path. So that's going to become our new stability axis in the x direction, right? Gamma 1 is the climb angle. So in this diagram, the aircraft is ascending, so you can see that with respect to the horizon line. And finally, the pitch angle is the angle which the body axis system makes with the horizon. So you can see that in this diagram, theta 1 is the sum of alpha 1 and gamma 1. So the stability axes are given subscript s's, so that's fairly intuitive, and we can see that we also have linear velocity components associated with those stability axes directions. So this is going to be our trim linear velocity, right? So in the stability axis system, the trim velocity has components u1, v1, w1, and so we assume that there's no velocity in the z direction, right? Because we've rotated the axis system, so we're not ascending or descending with respect to the z sub s axis. And we also assume that Vp, so the P in this final bullet point should be a subscript P, which, if you recall, is the velocity vector relating the body axis system with respect to the earth axis system for the trim condition. So that will just be equal to u, the component u, which is the x direction linear velocity component in the stability axis system for the trim condition. So basically all that means is that we're assuming the flight path is along the xs axis direction. Again, because we've rotated the body axis system to account for our trim angle of attack. And you can see that from the diagram on the left hand side. So finally then, we just need to discuss what we mean, well, what we're going to use as notation for our forces and moments. So as always, drag is parallel but opposite to the flight path direction or the free stream velocity, whichever you prefer, and we call the drag associated with the trim condition capital D subscript 1, as you can see at the bottom of the figure here. And that's going to be equal to the aerodynamic force in the x direction at the trim condition associated with the stability axis system. So obviously that's in the negative direction because it's acting backwards. So just be aware of all of these additional subscripts now and what they all mean. So add all of this stuff to your nomenclature list. And perpendicular to that drag component, we have the lift component, which is L subscript 1, and that's associated with the force, the aerodynamic force in the z direction for the trim condition in the stability axis. So F subscript A Z1 S. Okay, and then finally we have our aerodynamic moment. We have an aerodynamic pitching moment about the aircraft center of gravity, which we're going to call M, because that's the pitching moment, so the one associated with a rotation about the y-axis. And if you recall the conservation of angular momentum equations for a steady state condition, we saw that the aerodynamic and thrust moments in all three axes must balance. So the aerodynamic moments must be equal and opposite to the thrust moments in that particular axis. So that's all I have for the brief review here. Let's get stuck into deriving our equations for forces and moments.